Okay, so I hope the sound is good again, and we're going to continue to talk about energy and begin to talk about the law of conservation of energy. But before we can talk about the law of conservation of energy, we need to talk a little bit more about some other forms of energy and understand better this idea of gravitational potential energy. So again, we know our book uses a capital U for potential energy. So delta U, that Greek letter delta in front of it, remember we always look at that delta as meaning change in. So the change in potential energy, whether it's gravitational, elastic, whatever form, in a system is being defined as equal to the negative of the work done by the system's force. In other words, if I stretch a rubber band, okay, I am applying force to the rubber band and pulling it, and it's moving the direction I'm pulling. So I could look at that as me doing positive work on the rubber band and giving energy to the rubber band. In other words, positive work is giving of energy to something, and negative work is getting energy out of something. Now, if we were to look at the rubber band's point of view, the rubber band is pulling back against me while I'm moving its end further and further away. So it looks at itself as doing negative work. In other words, the force of the system is looked at by the system as doing negative work. And so the energy that ends up stored in the system, okay, is equal to the negative work done by the system's force. So in the case of the spring, as we talked about, the energy that ends up in the spring, the increase in energy that's stored in the spring, if I compress it, for example, that's going to be the negative of the work done by the spring. Okay, we've talked about the spring energy, elastic energies, rubber band, elastic, stretchy type energies like the spring. We want to talk a little bit more about what we want to do now is talk about gravitational energy and understand that a little bit more. So in this diagram, we see a bowling ball and it's being lifted up. Well, again, if I'm the one lifting it up, I'm putting a force upward on the bowling ball and moving it upward, so I look at it as doing positive work on the bowling ball. I'm giving energy to the bowling ball. On the other hand, the force in the system that we're interested in understanding here is the gravitational attraction between the bowling ball and the earth. And the gravitational force is pulling downward on the bowling ball. And so as I move it upward, that gravitational force is doing negative work on the bowling ball. Okay, so the negative of the work done by the gravitational force would actually be positive. And so we would expect this to end up increasing the potential energy of the bowling ball. We can see this if we actually do the math. If we look at the change in the potential energy, we just got done saying that will be the negative of the work done by the system force. So the system force here is the gravitational system, and the gravitational system is actually in the negative direction. But of course, delta y, the direction I'm moving it, is positive. So when we look at this integration from y initial to y final, we know that y initial is going to be smaller than y final. That is, we're moving it from some position y initial down here, maybe to some position y final up here. So y final y minus y initial would be positive. And so a negative times a positive, we're going to be integrating negatively. But when we integrate here, and my dy turns into a y, and I take y final minus y initial, remember I'm taking the negative of the work done. So the work done is negative, but the negative of the negative is going to give me positive work being done here, or an answer of positive, I should say, not positive work being done, but positive energy change. And so what we end up with is as y is increased, if delta y is positive, then delta U, the energy change, is going up. It's going to increase. If delta Y is negative, if we move the object downward, then delta U is going to be downward. We're going to get less energy at the end than we had at the beginning. So the potential energy of gravity is pretty much, we would just look at this as kind of being somewhat proportional to the object's height off of the ground or off of the zero level in the problem. The higher up it is off the zero level, the more potential energy the object has, at least as far as gravitational energy goes. Okay. Notice also that in this process of doing this integration on the work, notice that this term, once again, going back to this gravitational force right here, mg, that's steady throughout the problem. That's steady throughout the problem. And so, and notice when we integrate, we just get a y here. It doesn't talk anything about the path length or the path, the particular path it's taken. It just deals with our energy change is strictly, as we look at this right here, our energy change gravitationally is strictly the weight times the change in y. So it doesn't matter whether the bowling ball took a path, you know, upward like this and ended up here, or whether it took a path from right here directly up to that same location or height. It really doesn't matter which path it takes. It's only dependent on the initial position and the final position. So usually what we do to remember this and to understand this is we say, okay, the potential energy of gravity. So we use, again, a capital U here for potential energy, but then we put the little subscript G to remind ourselves that this is gravitational potential energy. And again, it's in standard units of joules, which we abbreviate with the J. Okay, the mass of the object in kilograms. G is the acceleration of gravity, which is always, always, always positive 9.8 meters per second squared. You just plug in a 9.8 everywhere you see a G. So that G right there is a 9.8. Okay, at least if we're on planet Earth it is. If we're on a different planet, it would be a different value. But on planet Earth, G is 9.8. And then Y is the height of the object. But the height of the object with respect to what? Okay, well, this is where it gets interesting. Because I can define Y whatever I want it to be. I can, you know, if I want to define my floor as 0 and I lay an object on the floor, then it has 0 gravitational energy. But if I want to put the object up on a table and I decide to call the tabletop my Y equals 0 height, then it has 0 energy there as well. So what's going on? You know, basically, it's only changes in gravitational energy that are meaningful. Okay, so again, if I call this the 0 height, which is what I'm doing in this particular example, then the bowling ball has 0 energy when it's down at the bottom. Okay, when it's on the 0 level. If I lift the bowling ball straight up to this height up here, and I'm told that it has 70 joules of energy up there, the question then becomes, okay, what if we take the same bowling ball, but this time we roll it up a hill on a path like that, up to the same height? How much energy is it going to have up here? You know, what's your answer up here? Fill it in. You know, write it down on your paper right now as you're following along. Then over here we have the same bowling ball again, or cannonball, whatever. I guess I called it a cannonball here. And the cannonball, if we look, we've got 1, 2, 3, 4, 5, 6, 7 equally spaced blocks high here. And we had 70 joules of energy if we lifted the bowling ball straight up to that height. And so the question is, how much energy will the bowling ball have after it's lifted up 1/7 of the distance, or 3/7 of the distance, or 5/7 of the distance, or 7/7 of the distance? Okay, so go ahead and fill your numbers in for those spots as well. And then answer the question at the bottom. When you're ready, flip the slide and check the answer. Okay, so hopefully you got these answers right. The bowling ball is going to have 70 joules of gravitational potential energy up at the top, no matter what path it takes to get there. Whether we have intermediate stops, like in the far right example, or whether we roll it up an unusually strange hill to the height, or just lift it straight up to that height. It's still going to end up with 70 joules, and the gravitational energy is proportional here, proportional to its height. So if the height changes, the gravitational energy changes proportionally. But again, the question then becomes, well, how do I know what to use as my Y equals 0 height? And the answer is interesting because it really won't matter. The exact amount of gravitational energy something has is not the issue. It could be any value you want. The change in the gravitational energy is what's physically significant. So gravitational energy, U sub G value, is not physically meaningful, because somebody could define their 0 level differently than me. Okay? So if I set a coffee cup, I told you the mass of the coffee cup, and I put it on the table and I said, here's the height of the table, what's its potential energy? Some of you might try to calculate mgh. Well, the point is, I can't really, or mg times the y position. But the point is, you can't really say exactly what the potential energy of the coffee cup is. There is no one right answer. If I make the top of the table where I set my coffee cup down as the zero height, then it has zero gravitational energy there, because mg times y, if my y is 0 at the height the coffee cup's at, it would have zero gravitational energy. On the other hand, somebody else might decide to call the floor the zero level, and if the cup's a meter high, then they would have the weight of the cup, mg, times 1 meter, because it's up at a height of y equals 1. And they would have a different answer. Their answer would certainly not be 0. So again, the actual value of the gravitational energy is not physically meaningful. What is physically meaningful is the change in the gravitational energy, and everybody should get the same answer for that. So here's an example from your book that kind of hopefully helps clarify all this, okay? So what we've got is a 2-kilogram sloth, whatever that is, it's some kind of little creature, and it's hanging 5 meters above the ground in this picture on a tree limb. And then it says, what is the gravitational potential energy, U, of the sloth Earth system if we take the reference point y equals 0 to be 0 at the ground? So in part A, we want to choose the ground as 0 down here. All right. In part B, then, they want to choose the balcony floor as 0, right? So we're going to use this height as our 0 height in the problem. In part 3, they say, hey, how about we take the limb as the 0 height? So where the sloth is right now is the 0 height. And then in part 4, we say, hey, what about 1 meter above the limb? What if we call that our 0 height right up there? So we're going to be looking at the gravitational potential energy of the sloth Earth system with different y equals 0 levels. And of course, when we do that, we're going to get different answers. Okay? So for example, in part A, if I look at the 0 height being down here, then the sloth is up at a height of 5 meters. And so mgy would be, taking m times g times y would be 2 times 9.8 times 5. And as you notice, I get an answer here of about 98 joules. So the sloth has a gravitational energy, according to part A of the problem, of 98 joules. The question is now, if we go to part B, is that answer still 98? And the answer is no, it's not. If I look at the value for part B, at part B of the problem, since the 0 height is here, the sloth is only at a height of 2 meters, and I only get 39 joules of energy. In part 3, where the 0 is here, the sloth is at 0, and so he has 0 joules of potential energy. And then in part 4, with the 0 all the way up here, the sloth is actually at y equals -1. And so in that situation, the sloth would actually have a gravitational energy that's negative. Which of these answers is right? What is the correct gravitational energy of the sloth? All could be right. All of them could be considered correct. Because we really have no absolute right answer as to where is the correct position of y equals 0. That is something we choose. We choose y equals 0. The thing is, once we choose y equals 0 in a problem, we cannot change it. So if we look at the change in the potential energy of the sloth, okay, everybody should agree on that. For example, in part A, if we knew the sloth started at ground 0 and climbed the tree and hung on the tree limb, then we know that the sloth, no matter what, was starting at this position and ending up at this position. Then in system 1, we would say, well, it started with 0 energy and it ended up with 98. So we would say the sloth gained 98 joules of potential energy. In system 2, where the 0 was here, we would say the sloth started at position -3 and ended up at position 5. So once again, his increase in energy would be 5 times mg, and we would get the same difference in energy. In other words, we would have 98 more joules here than we would have here. Okay, instead of this being 0 at the ground, it would be a negative number, and so on and so forth. So that's the interesting thing here. No matter what system we use, as your book does kind of the opposite, it says, okay, let's suppose the sloth drops to the ground now. For each reference frame, what's the change in the gravitational potential energy of the sloth system due to the fall? Well, in system 1, it's pretty clear that the change in position is from 5 meters high to 0, so it's going to be a -5. -5 is our change in position. And notice we get negative 98 joules. And that's going to be the case in every system. If that was 2 meters high in the coordinate system and then he ends up at -3, we still have a -5. That's still going to be a -5. In system 3, if he was started at height 0 and ended up at height 0, -5, then that's still a change of -5. We still get an answer of the same thing, right? And then this last one, if he starts at a height of -1 and ends up at a height of -6, once again, -5, -5. We get the same answer for the change in the gravitational energy of the sloth. Okay, so everybody, no matter what system, so even if every classmate in our class, even if every person in our class chose a different y = 0 height, we're all going to get the same gravitational change in the energy of the sloth. We're all going to say that the sloth has 98 joules less gravitational energy at the end. On the ground, okay? So no matter what system you had chosen, everybody should agree the sloth has 98 joules less gravitational energy on the ground than what he did hanging in that limb, right? Okay, that's the important thing here, all right? So let me erase that so you can see what that says better. And hopefully, as I do that, the key thing comes clear here. The amount of energy is relative to the reference frame. Everybody could have a different value, specific values of energy, but everybody gets the same change in energy. This is what's physically meaningful. That is the important thing in terms of why this conservation of energy is going to work. Okay. This slide I'm going to kind of skip past pretty quickly. We already did something like this previously where we derived the energy stored in a spring. Here what I'm doing is saying, well, any elastic material that has a linear restoring force will have a potential energy of the form 1/2 kx squared, where again, k is a description of the stiffness of the elastic material, right? K is a description of the stiffness of the elastic material. So basically, this is just a redo of something we did previously when we did it for the spring. We had derived that the energy stored in the spring, if we stretched it a distance x and had a spring constant k, the energy stored in the spring was u sub s, 1/2 kx squared. Well, if we have some other elastic material, maybe it is some kind of rubber or something like that, or stretchy nylon elastic, or whatever it might be, as long as it's linear. In other words, as long as the behavior is consistently proportional, then we can use this equation. Turns out, just so you know, most rubber is not linear in its behavior. In other words, if you stretch a rubber band, the force in a spring, a well-behaved spring, is directly proportional to the spring constant times the distance that we stretch it. So kx, and it's always in a direction to restore to its normal shape. Well, the force for a rubber band is going to have, it's going to again be a restoring force, so it will be a negative there, and we'd have some stiffness constant probably. But this formula here is not going to be x. It might be like x to the 2/3 or x to the 3/2 or something of that sort. It's not going to be quite linear. To be linear, this x has to be to the first power. That's what we mean by linear. In other words, if we make a graph of the force versus the distance, or force versus the stretch distance, we should get a straight line. Stiffer spring would be steeper, more gradual. Softer spring would be more shallow, but we would get a straight line, thus the term linear behavior. So x to the first power right here, that means that it's linear. So assuming the elastic restoring force is linear in behavior, this once again would be our potential energy term. So putting this all together, basically we're going to always assume linear behavior. Okay, we're always going to assume linear elastic materials. So if it talks about something being elastic, we're going to make the assumption that it's linear in its elasticity. So just like we had for the spring, we could now more generalize that and say, well, no matter what elastic material it is, whether it's a spring or whether it's stretchy fabric or whether it's a tree limb bending or whatever, if it's elastic, we're going to assume that the equation for potential energy is 1/2 kx squared, where x is the amount it's stretched and k is the stiffness constant. And so there you see it. This page kind of summarizes that. And we basically say, okay, let's just more generalize. Instead of just using an S for spring, let's just put an E there and say elastic potential energy. The elastic potential energy in something in joules is 1/2 kx squared. Okay. Now, one brief comment before we get into the law of conservation of energy. and that is conservative forces are forces that do not depend on the path. So gravity is a great example of what we call a conservative force. Okay, this is the term we use for forces that behave this way. If it's a conservative force, then that means that the work done or the energy change does not depend on the path length. And if we take a complete round trip, we should end up with zero work being done. In other words, no energy is lost or created in the process. So if we think about taking an object from point A and we move it along path 1 to point B, and we think about taking the object from point A along path 2 to B, then in this case, both paths generate the same amount of work done and the same energy change. And that means then if we take the object from point A to point B along this path, and then if we take it, back down to where it started from, right? If this path has the same energy change as this, going the same direction, then obviously if we go up, I get some positive energy change, and I come down, I would get the opposite energy change, and the overall effect is that a round trip gives zero work done. If the force behaves like that, such that it's not really dependent on the path, and a round trip gives zero work done, we call that a conservative force. We call that a conservative force. Okay? Conservative forces are path independent. They do not depend on the path. The amount of work done does not depend on the path. Now, there are forces such as friction, which are very much path dependent. Okay? But in the case of gravity, that's not the case. So if we look at a frictionless track, and I don't know why the book's choosing this here, but they say a slippery piece of cheese. Again, sometimes the crazier the example you come up with, the better you remember it. So let's suppose we have this 2-kilogram block of slippery cheese that slides down this frictionless track from A to B. Okay? The question is, it travels through a total distance of 2 meters along the track, okay, and a vertical distance of only 0.8 meters. How much work is done on the cheese by the gravitational force during the slide? So the cheese actually slides like this, and they're saying, hey, it's going like 2 meters along this track, but the vertical change is only 0.8 meters, 0.8 meters. And so when we go to do our calculation in the change in the gravitational energy, it's mg delta y, change in y, right, which again, you might want to in your notes to write that as y final minus y initial, because there should always be an initial position and a final. So here we're actually changing from a height that's higher down to one that's lower. And so delta y here is going to be negative. We're going to get a negative gravitational energy change. But the point is that I only need to use the 0.8. Its vertical height is all that matters. It doesn't matter how much it went sideways or what was going on sideways. Because if I move the cheese horizontally in my system, no gravitational energy change. Okay? It only depends on the vertical change. And so that vertical height change of 0.8 is all that really matters. It does not matter, okay, whether it moved horizontally. That's assuming this is frictionless, right? So the point is gravity is a conservative force, and therefore it doesn't matter, okay? Here's the thing. Here's the calculation of that, and the bottom line is that we get the same answer. The work done on the cheese is not affected by the gravitational force, because the gravitational force is always this way. So anytime the cheese, any component of the motion that was that way would be perpendicular to the direction of the force. And so, if it's perpendicular, remember our calculation for work is force. Remember, work was equal to the force times the distance or the displacement while the cheese or while the object moves times the cosine of the angle between. So if phi is 90 degrees, then of course there's no work being done. Well, any horizontal motion is going to be perpendicular to the gravitational force, and so we get a 90-degree angle with our system force of gravity all the time. And so the only change in height, the only thing that matters here is change in height. We don't have to worry about the horizontal change. That ends up being a wonderfully beautiful thing as we come into solving problems using the law of conservation of energy. So coming up here soon, in the next class or two, you'll see a beautiful application of this when we go to solve roller coaster problems and things like that. So before we stop here and take a break, an example of a force that's not conservative, which is called, obviously, kind of somewhat anticlimactically, it's called a non-conservative force. A non-conservative force is something that does depend on the path length for the amount of work done. So if we look at the kinetic friction moving a piece of chalk across a chalkboard, that obviously, the amount of, let's say, energy that it takes to move the chalk from one place to another on the board here. So if I'm moving the chalk and I'm moving it, like that, that's a different amount of energy than if I move it like that, which is a different amount of energy than if I move it like this, right? The path that I take on the chalkboard with the chalk, path A and path B will require different amounts of energy to get the piece of chalk to slide from point A to point B, or in other words, path A and path B. So even though I'm starting at this place and ending at this place, same beginning and end points, the amount of energy that's expended moving it over there is dependent on the path. So that is a non-conservative force. It takes more energy to move the chalk along this path to get it to there than it does to move it from there to there. So that is a non-conservative force. Conservative forces are cyclic, where if you move it back to the original position, it has the same amount of energy that it had when it started. Okay, so now what we're going to do is we're going to take a break and we're going to pull all this energy stuff together into a single comprehensive strategy for solving problems. So go ahead and take a brief break and we will pick up with that.